All right. So good morning, everybody. I'm trying to get in the habit of actually logging into all the online people before I start talking to you guys. So don't think I'm being mean or something. It is a bit weird to say good morning twice. So um, anyway, let me just make this little, put it somewhere. So today, so I guess the first thing is a few announcements. I did post the second homework, and that one is due on the 23rd. So that's next, so a little bit over a week. So as I mentioned here, so chapter 2 homework due 9/23. I also have a tentative date for midterm 1. And I'll send an announcement of, about this, but that'll be on the 12th of October. And so I'll also hand out a review document by the 28th. So in about 2 weeks, you'll have that. Okay. And I'll provide more details over the next few lectures about that. It seems like most people are getting straightened out with all the homework situation and accounts and all that. But if there's still some people struggling, just let me know. Send me an email. So the idea is we're going to continue today's lecture, moving into the topic of acceleration. We're going to spend the next 2 lectures finishing this chapter. Hopefully by Wednesday we will have finished it and maybe even moved on to chapter 3. So far, we're just because of the way the semester started and technology, all that kind of stuff. We're about a couple of lectures behind where I usually am around this point, but I do have a plan for how to kind of make up for it. And part of it will mean that the review sessions that I usually have in class, we'll do them virtually at a different time and probably with the help of a TA. But I'll give you guys that information so you can try to fit it into your schedule. So I guess let's begin with today's lecture then. And everybody that's online, just stop me and ask questions if you got them. But the main idea is we're going to look at this topic of acceleration. That's the topic of today. And I wanted to review a few of the other concepts, important concepts that we've covered so far that are going to be relevant for today. One of them is, this is the part where everybody that's online has to say, are you sharing your screen? Because we can't see anything. So you guys got to speak up, otherwise you miss all the stuff I'm writing. And I also got to get better at this. Okay. So hopefully now everybody can see my screen. So here's the announcements on the right-hand side. And also for people for everybody, if you haven't logged into your Reef or your iClicker account, please do so. Okay. So as I mentioned, some of the topics that we have covered already, we've covered things like displacement, which was the change in positions. And in the past few lectures, we've gone over velocity. And we know velocity, these are all vectors, by the way, delta x, your x in final and initial positions are also vectors. For velocity, we have that it's the change in position or the displacement divided by time. This is your velocity. And in terms of units, well, for displacement, we deal with this in meters. The abbreviation is m. For velocity, the units are meters per second. and you'll often see it written as m per s, so little s is seconds. And today, acceleration is a continuation of this, where we're going to go one more level. We're going to take velocity, or your change in velocity, and we're going to take that and divide it by time, okay? So this concept that we're going to talk about today is known as acceleration. And really, it's another way of saying change in velocity over some time interval. And so because of that, in terms of units, well, if you look at delta V, well, V has units of meters per second, and we're going to take that, divide by second. So technically, the units are meters per second. And so because it looks a little weird to have so many slashes in a name, we also, the accepted form is to write meters per second squared for the units. So it's saying every second that goes by, we're increasing our velocity by some amount given by that number that's going to go in front of that meters per second squared. And every second, we're increasing that amount. So if we have an acceleration of 5 meters per second squared, that means from 0 to 1 second, you go from 0 to 5 meters per second. From the next 1 to 2 seconds, you go to 10. And then the next second, you go to 15 meters per second, and so on. And so let's look at a few of the other properties. Much like when we had, slopes of position versus time giving you velocity, it turns out that the slope of a velocity versus time graph is going to give us acceleration. Okay, so, and hopefully it's easy to see, and part of it has to do with the expression, right? We know, as I said, acceleration is delta V over delta T. Well, in terms of slope, you guys remember it's, they always say rise over run, meaning it's the y-axis, some y-axis increment divided by some x-axis increment, okay? And so that's why you get in a velocity versus time graph, well, you get this interesting behavior because, if you've got velocity in meters per second versus time in seconds, then when you look at the slope, well, the y-axis is going to be meters per second, and then divided by x is per second. So you get the units correct. So like I said, or meters per second squared. So that part hopefully makes sense. We're looking at slopes, but now in the velocity graph, the slope of that is going to tell us acceleration. I did not mean to do that. Hold on. Okay. So, a real life example could be if you want to compare two vehicles. So in this case, they have a table for a Chevy Corvette and a Sonic. And it says here that, for example, for a Corvette, it says it can go from 0 to 60 miles an hour in 3.6 seconds. So Corvette goes from 0 to 60 miles per hour in 3.6 seconds. So this 3.6 seconds is our delta T. So if you were to write it down, basically initial velocity equals 0, final velocity equals 60 miles per hour, and delta T is 3.6. Whereas with the Sonic, and I usually ask people if they have a Sonic, they own one, but I notice people sometimes get a little bit shy because it's kind of not a very powerful car. It's super energy and gas and fuel efficient, but in terms of its capability of accelerating or speeding up, it can do 0 to 60, but it takes it a lot longer. It's going to take a whole 9 seconds to do it. And once again, you can break this down. Initial velocity 0, 60, delta T in this case is 9. And so you can do the math and say, okay, well, for the Corvette, if I want to find the acceleration, and we know it's delta V over delta T, which is final minus initial velocity over time, well, you end up getting 60 miles per hour minus 0 because we started at 0, right? And for the Corvette, and I'll put a little Corvette little symbol here, the time was 3.6 seconds. Now, you can't just divide that immediately, right? The units are off. That's miles per hour. So how do you deal with that? Well, you have to convert units first, right? So you can't just plug in the numbers and get the right answer, because here we have miles per hour and then seconds in the bottom. So like I said, we can't just take that 60. You have to first convert 60 miles per hour to something in meters per second. And we've talked about these conversions in the previous chapters. And so you have to know how many kilometers in a mile, how many seconds are in an hour, and set it up. And it turns out that when you do that, 60 miles an hour is right about 27 meters per second. So once you have your units correct, so good units, then you can plug it in and say acceleration of my Corvette is 27 meters per second over 3.6 seconds. And when you do that division, you end up getting 7.5 meters per second squared, okay? So what does that mean? Well, it means in terms of your time intervals, so if you look at time at 0, we have velocity equals 0, time equal 1, so this is time in seconds. We're moving at 7.5 meters per second. After 2 seconds, you add another 7.5 to that. So you're gonna get 15 meters per second. And you kind of get the idea, right? After 3 seconds, you add another 7.5, and now you're at 22.5 meters per second. And you could keep doing this, and then the next interesting thing is, well, what if you take those points and then you plot them? You're gonna get a relationship that tells you about the acceleration. So we'll come back to that in a second here. But let's do this example that is good practice for us to use this expression for acceleration we just came up with. So we're going to be using this delta V over time in this example. So in this example, 2.6 has something to do with the lion. It says lions, like most predators, are capable of very rapid starts. From rest, the lion can sustain an acceleration of 9.5 meters per second squared. So there's one key piece of information already. They're telling us it can do 9.5 meters per second squared for up to 1 second. So it can do this, but it's for 1 second maximum. After that, it gets tired, right? This is the reason why a lot of times, cats, like actual house cats, right? If you ever see them, sneak up to their prey, they do it very quietly because they need to be close enough so they can just do a quick burst and catch whatever they're chasing. Because if they have to run for too long, their muscles get tired. They're not built for long periods of super high energy. It's quick and fast, So I've got a cat that can swat flies out of the air, and that's a pretty quick cat, but I'm pretty sure it can't do that all day. It'll get tired. And so the idea here is you've got, I'm also a dog person too, so don't start making little ideas of what kind of person I am, right? I'm more of a dog person. That's a long story. Anyway, so it says here, the point of this is to find out how much time does it take the lion to go from rest to a typical speed of 10 miles an hour, which is the speed of a runner. So I guess the lions might be going after a person or something. So the idea here is, the goal is we want to, so if we transform that word problem into some symbols here, well, initial velocity is going to be 0, starting from rest. The final velocity we're going to get to is 4.5. So it turns out 10 miles an hour is the goal. When you convert this to meters per second, 10 miles an hour is the same thing as 4.5 meters per second, okay? And so our goal is to say, okay, well, given this information, how long will it take to get to 4.5 meters per second? So we have to take our expression for acceleration that's given here, and we want to solve for time, for delta t. In this case, we end up getting that delta t is equal to delta v over acceleration. And so if you plug those in here, you end up finding that, well, the change in velocity, since we're going from 0 to 4.5, it's going to be 4.5 meters per second minus 0, because that's the starting point, divided by the acceleration, which was given to us as 7.5 meters per second squared. So that 4.5 divided by 7.5 is, it's roughly half, right? So it's 0.47 seconds. So it's going to take half a second for that lion to speed up to about 10 miles an hour. So it doesn't matter if, how fast of a runner you are. If you're running, next to a lion that's hiding behind the bushes, it can, in half a second, it'll be going your speed. And if it was quiet enough and it managed to get close to you, then he might, bring you down and, have a snack for a week or something. The other thing that this problem is testing is, well, can we even get to that speed in that amount of time, right? Remember that that lion can only do that acceleration for 1 second. So if the speed that it needed to get up to was a lot higher, maybe instead of 4.5 meters per second, well, what if it was something like, I don't know, let's say it was like 12 meters per second or 15 meters per second. Well, now you need a little bit more time, right? So, well, let's make it easy. So instead of getting to 4.5, let's say we were going to twice that, to 9 meters per second. Under that same constant acceleration, if you do 9.5 divided by 7.5, you're going to get twice the time. So it's going to be like 0.94 seconds. And that's cutting it close, right? Because remember, after a second, he times out, right? He has to slow down. So he could probably speed up to twice that speed and it'll be fine. But if you want to go 3 times the speed, then that's when the line will slow down and it might not reach that velocity, or it won't reach that velocity in under a second. So let's go back to that problem with the car versus the Sonic. So remember we had this, we started writing down some of the acceleration for the Corvette, we had it there. And what they've done in the next slide here is they've made a plot of velocity versus time. And so for the Corvette, we remember those numbers. We know that after 1 second, we were able to go to 7.5. So this is on meters per second. This is time in seconds. And then after 2 seconds, we added another 7.5, so that brought us to about 15. After 3 seconds, we said we were at 22.5. And so you can imagine, we keep adding points here. And what you're doing in this case is you're starting to, all these points basically trace out a line. And this line of points, has a slope that gives you the acceleration of your object. So you could tell it's a relatively steep slope. And when you draw the slope for the Sonic, so this first one was for the Corvette. And then for the Sonic, you can see on the table there, after the first second, it's only going 3 meters per second. After 2 seconds, it gets to 6, and then 9, and then 12. So it's going to have a more shallow sort of line down here. So this is going to be the Sonic, which is slower. And so in this case, it has a more, so it's a smaller slope, which means we have a lower acceleration than we did for the Corvette. All right. So these are real things, the slope really does tell you the acceleration directly. So we're going to start getting into the habit of going from velocity to acceleration graphs. Much like you guys were doing position to velocity graphs, now we're doing it, but just a little bit, one level up. And so in that case, if you start with your velocity in meters per second versus time, you can see in this case, we first start off with one slope, so one kind of acceleration, and then at all of a sudden at one instant in time, we go to a flat sort of or a constant velocity, right? And after being at constant velocity for a while, our velocity decreases again and goes towards zero, kind of like that. So if we were going to make a plot of acceleration versus time, essentially it's a plot of slopes versus time, right? So that's what you want to do here for acceleration. So this is in meters per second squared. Whenever you see a graph like this, well, you want to say, okay, well, without even looking at any numbers, you can tell something about the slopes already. You know that for this first segment, we have a pretty steep slope, so it's some big positive number of some sort, and it's constant over that time interval. From 0 to whatever that first time point is where there's a change, we have a constant value, might be up here somewhere. So this is acceleration. And then for the next part, velocity is constant, so slope equals 0, which means acceleration equals 0. So all of a sudden we go to a state where for the next time segment, our acceleration's right here. Now the next part has velocity decreasing, so slope is negative. And you can look at the, if you look at the value of the slope, well, in the first case, it went all the way up to the top in one time tick mark. In the last segment, it's going from that constant value down to 0 in 2 tick marks. So we know that it's going to be, the acceleration in this case will be negative, and it'll be, since it's more shallow, it's going to be a lower magnitude than on the first side, right? So basically, out here, you're going to have a negative value for acceleration, and it's going to be only half the magnitude. So in this case, if we had, let's say maybe it was 2 of these tick marks to get to this, well, now on the negative side, the slope is lower value, so it's going to be about this right here. So you'd make a graph that looks kind of like this up until that point where we have measurements. So this would be the acceleration versus time graph that goes with the velocity time graph up above, okay? And I guess one thing to really think about is the fact that you can have motion, you can be moving at a velocity, at a constant velocity, even when your acceleration is 0. I mean, and this basically is it's the definition, right? Acceleration is just change in velocity. So even if you're going 60 miles an hour and you're not changing, your acceleration is technically 0, okay? So just keep that in mind. The acceleration doesn't necessarily tell you how fast you're moving. It just tells you how your speed is changing, whether it's increasing or decreasing, or not changing at all. All right. So also keeping in mind that we are dealing with vectors, this quick check kind of is a test of that. So in this case, it says a particle has velocity v as it moves from point 1 to point 2. The acceleration is shown. So what is the velocity vector that, as it moves away from point 2? So let's draw it out first and then talk about it a little bit. So essentially we have point 1, this is essentially the initial position. Point 2, this is the final position. At position 1, we have velocity vector number 1. And they've told us that the acceleration is in the opposite direction. So we've got a little acceleration vector there, okay? And just to make it more obvious, the velocity vector is definitely bigger than the acceleration vector, okay? Nice big vector. And so why am I drawing vectors and so obsessed about it? Well, if you remember the description, the equation that we're using that says acceleration delta v over delta t. Well, another way of thinking about this is this vector that we're going to get is really just final velocity minus initial velocity over time. And this delta t is just a constant. It's just a factor that you're multiplying by. So really, it's just this factor 1 over delta t times this change in velocity vectors. And really, this part here is the most crucial part, to realize that you're just looking at, the subtraction of two vectors to give you acceleration. So in this case, what they're asking for this problem for quick check 2.3 or 213 is really we want to find that final velocity vector. So you could rearrange this whole thing to say, well, if I solve for that vector, you're going to get acceleration times some factor t, and then you're going to get that quantity plus v initial is going to give you the final velocity vector. Okay, so really you're just adding the two vectors. You're adding v1 plus acceleration, which is in the opposite direction. So from that argument, you can expect that your velocity 2, or your final velocity, will be a vector that's also pointing down, but a little bit smaller. And it decreased by the amount that you subtracted, corresponding to A. So another way of thinking about this is anytime you see acceleration vectors, anytime you see these vectors, just always think about what is causing that acceleration. There's something causing it. It really is something like a push or a pull, right? When you speed up, you slam on the gas, the wheels propel you forward. You hit the brakes, well, there's something there that's pushing you, holding you from going forward. It's pushing in the opposite direction. So we're going to talk about this more in future. It turns out that this is what we call a force, but there's definitely a push or a pull acting on the object. And later on, we'll find that this is actually something called a force, and it's related to the acceleration. But always think about that. Whenever you see that red arrow for the acceleration, just remember it's like somebody just putting their hand and pushing in that direction. So if you're going that way and you get pushed the opposite direction, well, yeah, that's opposite acceleration makes you slow down. Similarly, if I'm running towards that wall and somebody pushes me from behind, well, I'm going to speed up, right? My velocity will increase. And so literally that acceleration vector is a push. It represents the pushing or pulling by something. So in this particular example, the correct answer was B, right? It was the only one that just changed the length of the velocity a little bit by the time it got to position 2. All right. So here's another question. So in this case, it says, so they're showing you a motion diagram, and it's just a good review for you guys to remember what these things look like and what information's in them. But it says here, they show a particle that's moving very slow, or that is slowing down. The sign of the position X and the sign of the velocity are blank. So let's see. So remember, they're asking about two things. They're asking about, so this is quick check 214. They're asking about position, and they're asking about velocity. All right. So let's start with position. So with position, the important thing here is to realize, where is X equals 0? Well, X equals 0 is on the left here. Positive values are to the right. So in this case, they've drawn the dots for the positions, and all these dots are to the right. So we can say, just from that analysis, well, all positions are positive. Cool. So we've got A or B to choose from now, right? So the next part has to do with velocity. If you look at the velocity, well, you have all these velocity vectors pointing to the left. That's to the left, and they're getting smaller over time, but they're all pointing to the left. So we can say all velocity here are negative. And so that narrows it down, and we find out that the answer is B. Okay? So a lot of these quick checks that are coming up are just a test of like the logic and the concepts to get to the answer. So in this problem, let's kind of read it and then work it together. It says here we have a ball moving to the right, and it's gonna traverse this ramp. And they want us to sketch a graph of the velocity versus time, and directly below it, using the same scale for the time axis, sketch a graph of the acceleration versus time. So let's go ahead and draw the problem. So we have our surface, starting point. Here's a little ramp. I'm gonna go down a ramp, and then we're gonna keep going, all right? And they start the ball up here at the top, and it says here it has some initial velocity that's greater than 0. We're gonna assume that there's no friction. They don't say it specifically, but the idea here is friction is something that will slow you down. So as long as there's not anything pushing on the ball, as it's going sideways, it's gonna have that same constant velocity up until it gets to that point where it's gonna start going down the ramp. And so what we're gonna do is, our goal here is, for this first part, is to draw, make a graph of velocity versus time. So, well, and we're gonna restrict ourselves to the velocity in the x direction, okay? Now, then you might be asking, well, whoa, hold on, it's gonna go down a ramp, that's not just the x direction, right? So up until this point, we can say that the velocity will be constant. There's nothing changing it. So here, this will have all value of v naught. But we know that once it starts going down the ramp, well, the velocity at the top might be something, and then by the time it gets to the bottom of this ramp, that velocity might be a lot bigger now, right? Huge velocity. But since we're only interested in plotting the x component, you have to remember that these diagonal velocities here have both a vx and a vy component, right? Similarly, at the bottom of the ramp, it'll have a larger vx component and a larger vy component. And we know this, right? You know, if you roll something down a hill, you've been down a slide, usually you speed up, right, as you're going down. Unless you're wearing shorts, right? And then you get caught and it sucks. So we know that's to be true. Now we get to the bottom of the ramp. Now we're on a flat surface. And so now the velocity won't change anymore. So that out here at this point, we're gonna continue with a velocity that's very similar to what it was right at the bottom of the ramp, okay? So how do we plot that? Well, we know that for this part where we're going down the ramp, we're speeding up, right? Our velocity is increasing. I did this last class too. I put them too close together. But the idea here is we're gonna go from a constant velocity, and then we're gonna increase to a new velocity, kind of upward a bit like that, right? So this is at the end of the ramp. So when we get to this point, we got right here. And then now for the rest of the time, we're moving at there's nothing slowing us down again. You just keep rolling off on this horizontal plane, and your velocity kind of goes like this. So this is the velocity profiles, these green lines that I've just drawn. And this is all still as a function of velocity. Okay, so the next part is to say, okay, well, now that I know the velocity profile going down, well, what does the acceleration look like? And well, in this case, now we're gonna plot acceleration in meters per second squared over time. And well, all you have to remember is that the slope of velocity versus time is gonna give acceleration. And this acceleration is what we keep calling A. And so that means we just go and look. We say, okay, well, first segment, we've got a flat line, right? Zero slope. So when you make a plot here, it's going to be 0. Acceleration equals 0. Next part of the motion, where we're going down the ramp, that's this little segment we're about to fill in. Well, now we've got a constant positive slope, right? So this right here, positive, and it's constant slope. So that means we're going to have a value that's up here, positive and constant, right? Once we get to the end of the ramp, once again, we get back to 0 slope, so we go back to 0 acceleration. So then your graph would look kind of like that, okay? So you could do a lot without even being given numbers, right? We can, this is all about understanding the relationship between acceleration, velocity. All right. So let's explore a little bit more this, the concept of the sign of the acceleration. So it says here, an object can move right or left or up or down while either speeding up or slowing down. Whether or not an object that is slowing down has a negative acceleration depends on the direction of the motion. Okay. So another way of saying that is so in the cartoon that they've drawn there, so let's make this situation number 1, where we are moving to the right. So this is a positive direction, and our arrows are getting bigger and bigger as we go, right? These are all velocities. And so in this case, I said, if you see velocity changing, in this case, it's changing to the right in that positive direction, well, that means we're going to have an acceleration that is in that same direction, okay? And because it's a positive acceleration, when you make your velocity versus time graph, you're going to see that it's going to be a constant slope plot. So this is velocity versus time. And we start off with a low velocity that gets bigger and bigger and bigger. And so that slope is telling you about the acceleration. So I meant to actually cover all those points, all right? Interestingly, you can have motion that's in the opposite direction. In the second situation, you can start off on the right-hand side with a high velocity. And as you keep moving, your velocity can keep getting smaller and smaller and smaller. Well, in this case, remembering that acceleration's acting on your object, well, it's making you slow down, so it means it's pushing against it in this kind of a fashion, right? It's moving in the opposite direction to that velocity. And once again, you can make a plot of velocity versus time. And you'd notice in this case, we're starting off with a very negative velocity. So we're starting off down here somewhere. And as time goes on, you get less negative, less negative, less negative as you get towards 0. And then this is going to have a certain slope to it. And in both cases, you can see I've drawn, need to get a bigger cursor here. You can tell that the acceleration is pointing to the right, has a certain slope. In the second case, acceleration is also pointing to the right, and both of these have the same slope. Even though one of them started with a negative velocity, they have the same slope, so they have the same acceleration, okay? So that's one example where we're starting from left to right, increasing velocity, and then on the other hand, you start from the opposite end and move to the left with decreasing velocity. There's another set of motions that have to do with acceleration going the other way, and that's what's shown here. So you can also have the situation, and I'll make this be situation number 3, where you start off on the left, and as you move to the right, your velocity gets smaller and smaller and smaller. Well, in this case, remembering that, something's got to be causing it to slow down. Well, acceleration is pushing against that velocity in that kind of manner. And then the fourth situation is just the other remaining one where you can start off from the right with a small velocity and work your way towards more and more negative velocities. And in this case, you also ask the question, well, what's making that velocity get larger in that direction? Well, it's the push being caused by this acceleration, right? Causing it to go that way. So in this case, you have the situation where both of these accelerations are moving in the same direction. And if you plot it, you expect to get the same slope, right? They're both pointing in the same direction. And so in this case, let's take a look. This is velocity in meters per second versus time in seconds. Well, you're going to get, for this case number 3, you start off high velocity. They're positive in all cases, but they're just getting smaller and smaller and smaller in magnitude to kind of trace out this kind of a slope. And you can tell right away it's a negative slope, so which matches the negative direction of the acceleration. Similarly, for the other example here, you start off with a negative velocity that gets more and more negative as time goes on. So this is time versus velocity. And it just keeps getting negative as you move. And so once again, you see that this has a negative slope, meaning that you're negative velocity like that, okay? So these are examples where you can have motion in opposite directions, but depending on how you're speeding up or slowing down, you can have the same acceleration. So these have exactly the same acceleration as did the previous example that I showed, which was this one. Except in this case, both accelerations are moving to the right. And in the second set of examples, both accelerations are moving to the left, all right? All right, so let's do some quick checks. Let's see we got this. So here it says, the motion diagram shows a particle that is slowing down. The sign of the acceleration is either positive or negative. Now this problem is a little bit, hopefully simple, because they've actually drawn the acceleration arrows for you. But you can imagine, you can actually answer this question even without the acceleration arrows, because all you need to see is, okay, well, where did we start? And so in this case, if we started off here on the right with a certain velocity, and that velocity is getting smaller and smaller in magnitude, but it's still negative, then right away we know something's got to be pushing against these to make them smaller. And that something has to be an acceleration that's pushing in the opposite direction, making it positive. All right. And obviously the cartoon has the orange arrows for acceleration in the positive direction. But you could have gotten it just from the velocity. All right. So this one's has a few more steps in it. But it says, a cyclist riding at 20 miles an hour sees a stop sign and actually comes to a complete stop in 4 seconds. And then at 6 seconds, he returns to a speed of 15 miles an hour, which is his motion diagram. So let's kind of think about what they're saying here. So it says first starts at 20 miles per hour. So that's velocity vector like that. He sees a stop sign. So now the velocity vectors have to get smaller. And eventually he's going to actually stop at some point. And then it says that after some time, in 6 seconds, he's going to return to a speed of 15. So now we're slowly going to speed up. But we're not going to speed up to the original size of the arrow, right? We're going to speed up to something that's a little bit smaller, maybe like that, that represents 15 miles per hour. So it'll look something like that. And so you have some velocities that give you choices that are kind of like that where you start off high, go to 0, and then you speed back up. The next question is, well, what do the accelerations look like? In this first segment, where we're slowing down to a final stop, well, slowing down means something's pushing in the opposite direction. So your acceleration's pushing to the left, opposite to the speed. And on the second part of the journey, we're speeding up, meaning the acceleration has to go to the right. So when you look at your choices, then hopefully that narrows it down. And most people chose the correct answer of B, right? You can see velocities getting small, gets to 0, and then speeds back up, but not quite to the original size or magnitude. And then the entire time, first half, you've got the accelerations to the left. Second half of the motion, the accelerations are pointing to the right. And if you look at all these carefully, you see some of these have the accelerations pointing the wrong way, or the velocities changing in a way that's different from what they explain. Okay. And yeah, so if you have copies of the slides on your own computer, I mean, it's better for you to make that bigger so you can see clearly the arrows, because they're a little small on the live screen. All right. I'm gonna skip this. All right. So here's another interesting example. So in this quick check, it says here, Mike jumps out of a tree and lands on a trampoline. The trampoline sags 2 feet before launching Mike back in the air. The question here is, at the very bottom, so when the trampoline is like stretched the most, what is Mike's acceleration? Is it positive, or is it upward, or is it downward, or is it 0? So let's see what you guys think about that. So first thing is, so they give us some background information. So there's this little tree here, and there's Crazy Mike gonna jump off. There's a little trampoline down here. But really what we want to find out, so we know that in terms of his velocity, it's gonna, the moment he jumps off, maybe he's going down kind of slow, gonna speed up, and he's gonna hit that trampoline at a kind of a high velocity, right? Depending on how high he jumped. But really what we want to focus on is that moment from when you first land on the trampoline. So let's say this is the trampoline. We have this large velocity, right? As a function of time, as this trampoline gets bent, it's gonna bend a little bit, it's gonna bend some more, it's gonna bend all the way down, and then it's gonna unbend and flatten out, right? That's what we know is gonna happen. So this is the trampoline surface. Well, we know that once you make contact, the next time point when you make velocity graph again, you're slowing down, right? Your velocity is gonna be a little smaller. When you get to the very bottom, you actually kind of stop, and then you're gonna start going up. Your velocity gets bigger and bigger, so that when you finally leave the surface, you've got this vector that's pointing in the opposite direction, but it's pretty big in magnitude, right? And so let's look at what's happening. You have these vectors here from high velocity to decreasing velocity. Well, what direction must the acceleration be pointing? Is it going to be pointing up or down? You're making these velocity vectors get smaller. What way do you have to push? Do you have to push downward on them, or do you have to push in the opposite direction? If I was going to slow you down, well, okay, first of all, let's ask the question. What is causing the acceleration? What's slowing you down? Is it a bird, a plane?
The resistance of the trampoline.
That's right. So it's a trampoline, right? Okay, so what direction is the trampoline pushing in on your feet or on his body? It's going to be pushing upward on him, right? You feel it pushing on you. If it was pushing you from the top, you would feel it on your head, right? So it's pushing you from the bottom. So that's the thing that's pushing. So in this part here, acceleration is pointing upward. It's against the direction of how velocity is changing, okay? Well, if you look at the second half of the motion here, well, what's causing you to speed up? You reach the very bottom. When you reach the very bottom, for a tiny, tiny instant of time, you switch between positive and negative velocity. So your velocity actually is 0 for a tiny instant in time, like instantaneously. And then you proceed to increasing your velocity upward. You start speeding up, You're going to leave the trampoline, maybe even bounce back up to the tree and to a branch or something. And so in this case, your acceleration is pointing up as well. So it turns out the entire path, we're pointing up, acceleration's pointing up. And if you focus in on these kind of 3 points where it's like right before, you point little vector, 0, and then upward, well, this entire time, you've got an upward pointing acceleration. So the entire time that trampoline is pushing on you upward. And so for this one, you get that's what the acceleration is. So it's a tricky one, right? Because you're going through all these different motions, slowing down, getting to the bottom, getting pushed up, but the entire time the trampoline is just doing its thing. It's just pushing against whatever's pushing on it. All right? So this is one way to kind of go about, you have to think about what the velocity is doing to figure out something about acceleration. All right, so let's do another problem here. So we're gonna do several of these, so fasten your seatbelts and get ready. So this is quick check 219. It says here, a cart slows down while moving away from the origin. What do the position and velocity graphs look like? So for this one, we have, there's two things we want to ask about. One of them is position, and that's going to be the blue curve. And then velocity, which is the green, well, it's hard to tell, but it's the green curve. This one's at the top, this one's at the bottom. But the idea here is, okay, well, if we look at, so let's look at velocity first, right? The first thing you want to do is find out, it says here it's moving away from the origin. And in the cartoon, it tells you it's moving to the right. So your little cart has this motion. And it also says, yeah, it says the cart slows down. So it's moving to the right, and the velocities, as time goes by, they keep getting smaller and smaller, right? It just slows down, but it keeps moving away. So in this case, we know all positions X are positive. Okay, so you can look at your graphs and say, okay, well, are there which ones are positive? And you'll see that B, C, and D are all positive. So we know that it's not gonna be A for sure. The next thing that we look at is the velocities. So the velocities, first of all, they're all positive, right? Because they're moving away from, so we're moving away from 0. So they're all positive velocities, but the velocities are decreasing, right? Because it says it's slowing down. So velocity is decreasing. So we want to look for a graph where all the velocities are positive and where they're decreasing. So if you look at that, well, all of a sudden it's not C. C has negative velocities. And what else we have? B, it's also not B because there's negative velocities there. And so by doing that process of elimination, you find out, as most of you have found out now, that the correct answer is D. This one has all positive, which is what we needed here. And it has velocities that are all positive and they're decreasing, right? So the graph for velocity versus time looks like this. So these are all positive and they're decreasing, okay? All right, let's do another one. So this one says a cart speeds up toward the origin. What do the position and velocity graphs look like? So once again, we're gonna do the same process. We're gonna start off. Here's our line for positions, and it says it's gonna speed up toward the origin. So we start off here with a small velocity, and after time, we get bigger and bigger velocities as we approach that 0. But in this case, just because we're on the right-hand side, we know that all positions are positive. We know all velocities are negative, and we know that the velocities are becoming more negative, right? So becoming more negative. Another way of saying this is the magnitude of those velocities is increasing. So we want to look for graphs that do this. So right away, you eliminate the positions that are negative. So that gets rid of A, gets rid of, oh, just A. But then the velocities, you look for the ones that are all negative. So for negative ones, we have some in B and we have some in C. But then the next part is to say, we need to make sure that they're becoming more and more negative as time goes by. And the only one that does that is going to be C, right? So that's our answer. Okay. Questions? Let's do a few more of these. So in this case, it says, a cart speeds up while moving away from the origin. What do the velocity and acceleration graphs look like? So this one's a bit different now, right? Instead of position and velocity, they're asking about velocity and acceleration. So quick check, 221. So let's draw it out again. We're moving away from the origin towards the positive x direction. And it says it speeds up. So initially we have a small velocity and it's going to keep getting bigger and bigger as we move along the x. So that's one thing to look out for. And because the speed is increasing, that means that we also have an acceleration that's constant. So basically, and the reason it's constant is because this acceleration is giving you it's a weird thing to think about, but it's a constant change in velocity. Velocity is, it keeps increasing, basically. So the velocity is not going to just stay constant all of a sudden and then decrease. The entire time, velocity is just increasing. So you need to have, so because of that, you're going to need a positive acceleration, and it has to be constant. So when you look at the options here, well, we have some with increasing velocity. We have B and C and D all have positive increasing velocities. So B, C, D all have V increasing. But we need to match it with the one that has constant positive acceleration. So in that case, when you look at those, you're going to get a few options. And it turns out in this case, most people chose B, and it's B. You can see it's positive, constant acceleration. And I do apologize. I mean, you really want to be looking at the slides on your own computer or print it out, because then you can actually see the labels a little bit better. Okay. All right. So let's do another one. So in this case, it says, we have a motion diagram of a car speeding up on a straight road. So what is the direction or the sign of the acceleration? So once again, you always keep track of where do we have x equals 0, positive x is out here. And so because we're starting up on the right-hand side and we're moving towards 0, all these velocities that keep getting bigger and bigger in magnitude are all negative velocities. And because they're increasing in that direction, that means, so well, something's got to push them to speed up, right? So we have acceleration has to be in that direction as well. And that direction, turns out, is a negative acceleration. Okay? So, yeah. All right, so in this problem, it says, a cart slows down while moving away from the origin. What do the velocity and acceleration graphs look like? So let's work on this one now. This quick check 223. So once again, you always want to draw the problem. So we're moving in the positive direction. So it slows down and it's moving away from the origin. So slows down means start with big velocities, you get smaller velocities after time. And so the question then is, well, what's causing those velocities to decrease? It's got to be an acceleration in the opposite direction that's making them slow down. So you have something that looks like that. And in this case, it's going to be a constant, and it's going to be negative. And for the velocities, they're going to be positive and decreasing. So you're going to have, for velocity versus time, a situation where you start off positive and you decrease, at different times. Similarly, you see that's a constant negative slope. So when you plot the acceleration, it's going to be a constant value, and it's going to be negative down here somewhere. Okay, so for this problem, everybody chose C, and it is in fact C. Okay. All right. Almost done with these, but they're all related, so it's good to get practice with all these different situations. In this problem, it says a cart speeds up while moving toward the origin. What do the velocity and acceleration graphs look like? So just another one of the same kind, just different starting conditions. So in this case, we have it's moving towards the origin, and it starts out here in the positive x side. And now because it's speeding up, your velocities can get larger in magnitude, even though they're negative the entire time. And so whenever you have that situation, once again, we ask the question, what's causing that velocity to increase that way? Well, something's pushing it in that direction, and it's the acceleration. Once again, acceleration pushing to the left. So for this problem, we can say we have acceleration that's constant, and it's negative. For the velocity, we're going to have, they're going to be all negative, and they're going to be increasing in magnitude. So basically becoming more negative. So when you make that plot, once again, you got velocity versus time, you got acceleration versus time. For the velocity, just looking at the graphs here, we know we're going to start off, they're going to be all negative. They're going to become more and more negative. So it's going to look kind of like that. So this is the velocity part. And for acceleration, once again, it's also negative, and it's a constant value. So the acceleration will be something that kind of looks like that, some negative acceleration value. So this line right here is the acceleration equals 0 line. So considering all those requirements, then that means that the correct answer ends up being C. Okay, all negative velocities, increasing magnitude, and then constant negative acceleration. All right, so now let's look at how to go from acceleration to velocity graphs in this example. So in this example, they've given us an acceleration, and they're asking which is the correct velocity versus time graph. So let's go ahead and put our starting acceleration here. We're going to have initially a negative value for our acceleration. And then all of a sudden, for some reason, we have suddenly a positive acceleration. And this is acceleration in meters per second squared. All right. So remember, these values, when you put them on a velocity versus time graph, they are going to be the slope of that velocity versus time graph. So just looking at this, well, this is a negative slope. So for this value here, I'm just going to do it out here without axes, is going to give you a negative slope. This is a negative velocity. Once we get to that point, we have a positive velocity, so positive slope. So we're going to have something that looks like this. And this, so that little line here is the place where things suddenly switch. So when you look at your options, well, there's only one that has that shape, right? That has that negative slope and then positive slope. And the one that does that is option E. And so one thing, so the reason I put it here on the side is because, yeah, I mean, this is the right answer. It's going to give you negative and then positive slope. That kind of matches this business here. But unless they give us extra information, you could have had another graph that would have been acceptable, could have started with the velocity, instead of being at 0, could start positive, gone down to a lower positive value, and then gone back up, kind of like that. That also would be okay. It just wasn't one of the options, but you were looking for that shape. All right. And I guess I didn't let you guys pick, but there you go. Let's see. So in the remaining minutes, we're gonna now move on to developing equations for motion with constant acceleration. So we'll see where we leave off here, but this is gonna be motion with constant acceleration. And in all problems in this class, anytime you've got an acceleration that's there for the whole problem, that acceleration is always going to be constant. It'll be a rare thing for you guys to ever see an acceleration graph that has like lines with like slopes in them. Acceleration graphs are always going to be like flat lines that are either positive or negative. Okay, so just I guess keep that in mind. But the idea here is now we're going to take, we're going to start, developing the equations we need to deal with real problems. And in the problem here, they show an example of motion with constant acceleration. There's a rocket taking off. So even though this is a rocket from like when they were launching rockets in like the 70s and 80s, mainly, nowadays, right, you've got SpaceX and Elon Musk and his big rockets down somewhere in Texas launching these things that look like, grain silos and stuff. I mean, pretty spectacular. And so this field is kind of alive and healthy. And this is just one example. It's like an engineering rocket kind of example. But later we'll do other examples that are maybe more relevant to you guys. You can imagine anytime you have motion that is changing, that's going to be the case. Okay. So in this case, they have this example of a rocket that starts off, you can see that it starts off at a low velocity at some initial times. And then it's, in this case, I think the time is I think it's in minutes. Yeah, in seconds. Actually, that makes more sense. And so in this case, at time equal to 0.5 seconds, we're moving something like at at 0.5 seconds, we're moving at about something like, looks like around 10. And then by the end of the motion, by 2 seconds, there's a lot of points here that they've plotted, but by the time you get to 2 seconds, you're somewhere in the 30s in your velocity. So this is velocity in meters per second. So you have these you trace out these points. So every time that a second goes by, you increase your velocity by a certain amount. And so in this case, we're looking at so keeping in mind accelerations, delta V. In this case, it's going to be the vertical, so we'll put a little y on there over time. So for this problem, you can see they're choosing initial time of 0.5 seconds, a final time, t final, of 2 seconds, so that your delta t, final minus initial, is 2 minus 0.5, which is 1.5 seconds. And then for the delta v that goes to this equation, well, since we decided to make our region that we're collecting information be from this initial point to this final point, well, that also carries with it some v initial. And up at the end of our trajectory, we got some sort of v final. And in this example, when they do the delta V part, which is the final minus the initial, it turns out that those numbers give you a difference of about 27 meters per second. So that's the distance between those two right there, the delta V. Okay? And so when you get the acceleration, well, you're just going to put that 27 meter per second difference divided by the 1.5 second difference, and that's going to give you 18 meters per second squared. So this tells you that every second that goes by, you increase your speed by 18 meters per second. So the first second is 18, and then, multiply times 2, 36, etc. So the other nice thing that we could do is we can develop what I'm going to call the first kinematic equation. So using the information here of acceleration is equal to delta V. And if we confine ourselves to one direction, you put a little x, but I just won't write it because I don't want to. Using this expression, we're going to find the first of our kinematic equations. And it turns out there's going to be 3 of them, and we'll get to them, we'll develop them all. But in this case, to get the first kinematic equation, the way we do that is, first of all, we're going to say, okay, well, that delta V, remembering that delta V is equal to the final minus the initial, you can plug that in there. So you're going to get V final minus V initial over delta T. And what we're going to do now is we're going to solve for final velocity. So if you do that, you're going to get A times delta T, and then you're going to add to that V initial, and that's going to put final velocity off by itself. So this expression that I've written here is what's going to form the first kinematic equation. So kinematic equation number 1, okay? So in other words, if somebody gives you the starting conditions, maybe you start at 0, they tell you the acceleration, they tell you the time, guess what? You can figure out the final velocity for whatever time they're asking you to calculate it, okay? Now, there's another one that we're going to discuss further, and this one's going to be, so kinematic equation 2, and this is where we're going to pick up next time. It's going to ask you to remember that the area under a velocity versus time graph, do you guys remember what it gives you? Dun, dun, dun. Anybody remember that? What do you get from the area of a velocity time graph? I'll make it awkward, I'll wait. See somebody tell me an answer. So let me give you a hint. Or if somebody's online and wants to say it, say it. So remember area. Remember if you had something that looked like this, we're asking about this thing. Well, if you look at units, you're doing meters per second times seconds, right? Seconds cancel, you're gonna get meters. What property have we discussed that has units of meters?
Is it distance?
Yeah, so distance is one of them, but in terms of these vector quantities, it's the displacement. So that's what we're going to get to next time. We're gonna analyze these kinds of graphs, and we're gonna have something where you might have motion that looks like this. We already know that the slope of a velocity graph is gonna give you acceleration. But in this case, the area, everything under here is gonna give you the displacement, that delta X quantity that we talk about. And furthermore, and if you're interested in this, I mean, you can look ahead, but this is where we're gonna pick up next time. Well, we're gonna take these graphs and say, okay, well, maybe I'm interested only in this region from T initial to T final. So in this case, we might only be interested in this area. And you know, if you look at it, well, this is actually two different shapes, right? You've got the shape of a rectangle plus the shape of a triangle. So we're going to find out that our delta x is going to be the area of the rectangle, which is number 1, plus the area of the triangle, which is the one I labeled as 2. And so using that information, we're actually going to build an equation that tells you how to do it. So that's all for today, guys. And if there's any questions, ask away. If not, we're done for today, and we'll see you on Wednesday.
You said earlier that you got a tentative date for the exam. Could you tell us that? I forgot.
Yeah, so I mentioned it's the tentative data is the 12th of October. And then on the 28th, I'll hand out, or before the 28th, I'll hang out a review document. Okay.
I'm sorry, can you repeat the question and then the answer too?
Oh, sorry. The question was, you know, earlier in class, I mentioned tentative dates for the exam. So they asked, what's the tentative date? And I had said earlier in class that it's on the 12th of October. And I will hand out a review document a couple of weeks before that date.
Thank you.
Sorry. And have you decided yet, by chance, how the test will be?
Short answer is no. I will give more details in the following lectures.
Okay. All right.
Okay. Cool.
Thank you.
Thank you. Bye. All right. I'm going to log out now.